When people vote, the biggest challenge for those running the election is to prove that the candidates who lost actually lost. In paper-based elections worldwide, a process has been in place for 150 years so that those concerned about the conduct of the election can really see what is going on and be satisfied with the results. As populations have grown and as other government paper processes have been automated with computers, electronic voting has been created.
You have chosen Susan.
This has led to many improvements in elections. For example, computers can help people who cannot read to mark the ballot. Votes collected with computers can be counted electronically.
Susan wins.
However, this has created new risks. Actually proving to Jamie that he did not win becomes very difficult because the votes are not on paper. Casting a paper vote is very simple. It is obvious the vote has made it into the box. Casting an electronic vote with the same level of safety as the paper vote has been described as the hardest transaction to automate in all of computer science. The electronic vote must be protected for transport, so it cannot be read or changed, and it must be impossible to connect the voter with this vote. And like the security of the ballot box padlock, it must be possible to prove the vote is secret, safe, and private. Unfortunately, because we are attempting so many things together, electronic voting is most susceptible to system bugs, failures, and malfeasance at this particular point. So, in order to prove to Jamie that he definitely did not win, some electronic voting systems have had to reintroduce the election steps of the paper system. For example, some voting computers send the vote electronically but also print out a paper copy. This is a form of verification because the voter has something meaningful to check. If the paper copy is wrong, she can see it herself and alert others. This also reintroduces some of the constraints of paper voting. Namely, you need to be able to read to confirm the printout is the same as that on the screen. And this printed ballot cannot be taken away by the voter as a receipt. It must stay at the polling place because the voter's vote must remain secret from others. To prove to Jamie the computers have done the right thing, some of the computers are chosen for an audit, and the printouts are hand-counted to confirm they match totals reported by that computer. Unfortunately, this means elections now run both paper and electronic processes, and that makes everything even more complex. It would be better if the system could be all electronic, but with convincing proof that the computer has operated correctly. This is where COASCA comes in. COASCA is a voting system that changes the way electronic votes are cast, so that capture of votes is simpler and safer and can be more easily proven to the voter without having to do both paper and electronic ballots. COASCA does use some paper receipts for verification, but they can be optionally discarded by the voter. COASCA creates a temporary list of the election candidate names in a shuffled order. This order is different for each voter, and only the voter sees this order. The voting computer reads this order. The computer prints a voting receipt. The receipt is the voter's choices, but in the shuffled order. Even though the voters saw the official ballot order on screen, here they verify their vote is correct even with a list of shuffled names. The list of names is destroyed, so it remains a secret. The printed receipt can be taken home by the voter. Missing the shuffled names, the receipt does not reveal to anyone else how the voter actually voted. A code on the receipt allows the electoral authority to reorder the receipt back to the legal ballot order, which then reveals the vote for counting. A copy of the receipt is taken by the computer and sent to the central system. However, this time, the networks are not carrying votes, just receipts. Our voter can go home and look up her receipt to confirm it is among those on the central system. She can also examine the receipt, which is signed, to confirm it has been recorded by the electoral authority. At the end of the election, observers and the election authority provide devices that cooperate to reveal the shuffle orders, allowing the reordering of those receipts back to countable votes. How does COASCA actually show that all the votes got recorded as the voters wanted and that all the recorded votes got processed and included in the count without any votes changing. Let's vote, this time with some trouble thrown in. We will see how it is impossible for loss or damage to occur undetected. The list of shuffled candidate names, which is how COASCA protects the final vote, can be examined to confirm that it is an official list. This is similar to the way paper ballots are securely printed and checked before an election. These lists are made well before the election. A selection of them is audited to make sure the shuffled order can be undone correctly back to the legal order. It is not possible for this voting system to create more electronic ballots during the election than those that were made in advance of the election. The list of shuffled candidate names can be audited by the voter in case the voter does not believe the displayed order of the candidate is correct, or that the order in the QR code may be different. However, the challenged list cannot now be used to vote because its order is no longer a secret. So the voter gets another list and can vote with it or challenge that list as well. This can be repeated as many times as the voter wants. Finally, the voter is confident the ballots are correct. The voting receipt can be electronically examined to confirm it has been centrally recorded by the electoral authority as cast. All the receipts can be observed on the network. They can be observed at the central location. No one can see the actual votes. No encryption of the network is needed because the receipts already protect the votes. In fact, the central location is just a public website. All the receipts are made public. A day's set of receipts is signed as a batch. Voters and anyone can look up individual receipts in a batch. The voter can compare this to her printed receipt to confirm her vote is unchanged and remains amongst those collected. Voters checking are very likely to find any lost or damaged receipts. Unless there are any reported issues after the close of the election, independent election key holders convene. Each has a key they made for themselves and the key that they gave us to make the blank ballots. Only by coming together can they process the receipts back into votes we can count. These are the secret positions which each give the correct location of the candidate names. When we go get these for all receipts, then we shuffle the batch so the votes we decrypt can't be linked back to the receipts. If you voted first on this system, we don't want your vote to be decrypted first, or this would put your privacy at risk. We are going to illustrate the vote this time as a preference order rather than a simple X. This way you can see how the whole ballot is protected, not just the single mark the voter makes. So let's say the voter provided a preference order vote with 4 choices in order. We will reorder these blue numbers to the voter's preference order, and we are done with the receipt. This is all we need to get back the voted list. Now we recover the legal order of the shuffled list. We show how math is the key to this. In the following examples, we are using only very small numbers. In a real election, these numbers are 100 digits long. Each of the key holders performs their part of the decryption. They do it like this. We take the first secret position. Our key holder uses their private key, which is just a number they know. We take the public key, which did the encryption. The first key holder does this. We need at least 3 key holders. The other 2 key holders do the same with their keys. So we have 3 values, 41, 16, and 21. Now we combine them. That's our combined decryption. Now we get the secret and use it. So this is candidate number 2, which is Jamie. He gets the voter's third preference. The key holders repeat the math the same way to get the rest of the ballot, which is 2, 1, 4, 3. And there's the vote we can count. This is done for all the receipts. They are hand counted or the vote data are machine counted. But how does Jamie know the key holders did the right thing with each math operation? Each key holder has to emit a proof at each step. Since decryption is just math, we can actually provide some of the details of the steps they used just to show it was done right, but without giving away the private keys the key holders have. Why don't we just hand over the private keys so you and I can do our own decrypt? The answer is that decrypt must happen under conditions where the keys cannot be used to align any one receipt with its vote. If anyone had the keys after the election, they could go back and work out what your vote was from your receipt. So instead, we are going to make the key holders give us some of their workings, just enough to show they did the right thing.
Here is an analogy for how this works. Imagine that you are a teacher in a classroom and that you have given your children a hidden word puzzle. You've promised that the first child who can find all the names of the animals in the letter grid on the blackboard can have a prize. The problem this creates is, how can you know whether a child has completely solved the puzzle and found all the words? One child might put up his hand without seeing all the animal names. Another might include some words which aren't animals. What you need is a way to quickly check a child's work without her calling out the names of the animals or revealing the position of the words to the other students. To achieve this, you give them a simple test. You ask them to tell you the total number of vowels and consonants in the animal words that they have discovered. The children who have missed words will have too few. The children who have included wrong words will have too many.
We are going to do the same with decryption of votes, but we are going to do it with math. We just have to calculate a math total and check it matches a replay of the decryption, and we know the key holders did the right job. To allow this, the key holders expose some information, but not their secret keys. To make the third number, we need a random number. We roll the dice. So we can publish these 6 numbers. That's our proof for this key holder's work on this ballot position. The key holder has shown us the image of the fox, but without giving away the secret. Jamie will now check that it is indeed the fox. He can calculate a product, which can only be correct if key holder 1 did the math exactly right. We take our original public key part, which is 16, and the second part of the check is 41. So this proves the key holder arrived at the products he published, 35 and 41, by performing the math behind them correctly. Jamie can perform this math on all the ballots if he wants. Maybe you don't get all the math in this animation, but we hope you can see that it's only math, multiplication and addition, that Kowalski uses to give you extremely strong proof that all is well and figures don't lie.
All of the proofs described in this animation are made public along with the receipts and the final votes. Anyone can use their own tools or tools from the internet to check the calculations performed in the election. It's not possible for votes to be damaged, lost, or changed without these calculations also failing. Alaska is an international provider of verified electronic voting systems. All are free open source software.